Good morning and thank you for joining us today. The webinar will begin momentarily. Your host is Chi Bin La today. Additionally to the chat, you can also submit questions via the Q&A function. Today's webinar will be recorded and a link will be sent out to all participants. So without further ado, let's begin.
Hi everyone, welcome to this edition of the IAV webinar series. My name is Chi Bin La and I am responsible for powertrain controls and calibration at IAV in the US. You can contact me at IAV via the email address chi.la@iav-usa.com or via our general email address info@iav-usa.com. In today's webinar, I will be covering the topic of model-based calibration using dynamic design of experiments. In summary, we will discuss what is model-based calibration, the evolution of model-based calibration from steady state to dynamic DoE. We will then review the overall calibration process, discussing its benefits, and finish off with a summary of model-based calibration. Today's presentation will last around 10 minutes. During the presentation, we will keep the chat function found at the lower right of your screen open for questions, such that at the end of the presentation, there will be a 10-minute session to address your questions. Also, please look out for more webinars in the series. Details can be found on our Twitter page at twitter.com/IAV_USA. I will start the presentation with a short video introducing IAV. So please continue to watch, and I hope you find this webinar interesting.
IAV expertise can be found all over the road. There's no such thing as an IAV car, but almost every passenger car utilizes IAV technology. For instance, in the chassis, in drive mechanisms and engines, in the vehicle's electronics, in body structures, and in its safety systems. IAV develops innovative solutions for the entire vehicle and for almost every automobile manufacturer. IAV also has state-of-the-art facilities for testing everything on wheels, whether passenger car or commercial vehicle, fuel-powered or electric. Exciting activities covering every part of the vehicle. That's IAV.
Now that you know a little more about IAV overall, let's return to the discussion on model-based calibration using dynamic DoE. In order to meet demands for high efficiency and low emissions, modern engines are becoming increasingly complex. As such, there are a multitude of control values that need to be calibrated for the complete speed and load map, including variables that control the air charge to ones that manage the fueling. The optimal setting for these variables, of course, needs to be done with the appropriate balance and trade-off for multivariate targets. These targets can range from overall fuel efficiency to specific emissions constituents or constraints on temperature for reasons of durability. Model-based calibration allows multi-objective optimizations and enables a high level of understanding between the trade-offs of fuel consumption and emissions. The standard full factorial calibration method is very time-consuming when there are a high number of parameters. It is difficult to optimize against a global target. As such, the individual operating points are optimized, and changes in the system requires recalibration. The traditional steady-state DoE calibration method improves this and can reduce overall calibration time by as much as 60 to 70%. Because it's model-based, one can do true multi-objective optimization, including those for global targets. The calibration model can be reused in different applications without the need for recalibration using online modeling tools provided by IAV. However, steady-state DOEs are insufficient for the simulation of dynamic processes. For example, exhaust gas emissions that closely match drive cycles or real-world transient operation. IAV has shown in the past that the dynamic DOE calibration method can provide a model that accurately predicts the transient response of the engine. Furthermore, the resultant dynamic model can be utilized for controls development. The dynamic DoE calibration process is similar to that of the steady-state DoE in that the overall engine map is divided into different zones based on the operating range and drive cycles. Operating limits for each calibration variable is quantified using the advanced boundary finder, resulting in a convex hull that defines the safe operating envelope. Where the dynamic DoE process differs is that instead of testing at defined steady-state speed and load points, the test plan is comprised of frequency-varying sinusoids representing each of the calibration variable. These sinusoids are then scaled by the convex hull, such that during calibration, all of the parameters are simultaneously varied on a continuous basis. Additionally, steady-state as well as ramp and hold test points can also be included. The result is a dynamic calibration model that is derived from the transient operation of the engine. The advantage of the dynamic model is less measurement time, although the trade-off is a higher degree of upfront modeling and a higher demand on the test bench. The resultant model is of high quality for both steady-state and transient operation. If included in the test plan, the temperature influence, such as cold start emissions, is also possible. And since the model accurately represents the engine, it can serve as a plant model for controls development. Using a model-based calibration approach permits the global optimization of cycles, as well as the calibration of dynamic functions, such as time to torque or temperature influence during cold starts. Model-based calibration, specifically model-based calibration using dynamic DoE, provides results that accurately depicts the true engine response during transient operation. Because of this, a further application of dynamic DoE model is to be able to link it to the actual control strategy in a model-in-loop environment. The dynamic DoE model serves as a fast and accurate plant model to help develop the ECU control strategy, permitting the use of optimization routines to calibrate the parameters offline without further engine testing. This was the first presentation on dynamic DoE for model-based calibration. Other upcoming webinars will go into the details of how to set up the model and define constraints, application of the advanced boundary finder, and how to perform optimization with examples. Other topics included in the webinar series includes pre-PVE automation with IncaFlow, mill-sill hill simulation using Velodyne, virtual field testing approach, robust OBD calibration, and hybrid emissions model. For a complete list of topics and services that IAV provides, please visit us at our webpage at iav.com. I want to thank everyone for the interest in IAV and our capability in model-based calibration. If you would like to discuss these topics in more depth, then please feel free to contact me via the email address chi.la@iav-usa.com or via our general email info@iav-usa.com. Also, please look out for more webinars in this series. Details can be found on our Twitter page. Now that we've concluded the presentation, let's take a few minutes to answer your questions.
Hi, everyone. So we'll take a few minutes and go through some of the questions that have been submitted. I'll read the questions out loud because I'm not sure that everybody has access to them. But the first question is, how much savings in test cell time can be expected over a steady-state DoE calibration? I guess that's an obvious benefit of dynamic DoE is the test cell savings time as well as the quality of the model. Given the complexity of today's engines, the move from the full factorial calibration to a model-based calibration, such as the often used steady-state DoE, already provides a fairly significant savings in test cell time, upwards of 60 to 70%. moving from a steady state calibration method to a dynamic DoE calibration method gives us further time savings, and we've been able to demonstrate that we can save upwards of an additional 50% savings in time. But we need to note that although you save a lot of time in a test cell, there is an increase in the offline engineering effort that's required, meaning that all the work that's being done outside the test cell to define like the design space, setting up the test parameters, and that all of this now requires a higher level of expertise from the engineer, and it requires an engineer that understands both the calibration process, how the engine reacts, as well as how the test cell operates. So, the trade-off here is shorter test cell time, better quality model, but a higher degree of engineering effort that's required. So the next question is model-based calibration using this dynamic process? Is this a tool, or is this a service that Ivy provides? And the answer to that is that Ivy, we've been maturing the dynamic DoE calibration process for well over a decade now. We've successfully applied it on everything from early development programs to those where the calibration actually goes into a final production release. So the answer kind of depends on the request from the customer. The dynamic DoE can be provided as a complete turnkey system. So both the method, the process, the tool suite, all of that can be integrated into the customer's test facility. Or it can also be done as a service by IV. So we can do it via the testing here at our facilities in Northville, Michigan, and during the course of the project execution, we can also provide hands-on training to the customer as well, in case that you wish to do that yourself the next time around. There's a question on what is meant by dynamic DoE having a higher demand on the test bench. So if we look at the current calibration method, it basically entails bringing the engine to a predetermined condition. Usually the condition is based on a set engine speed and engine load, and then you adjust the calibration variables to get to a certain state that you want. And at the same time, you've got a desired fixed coolant temp and engine oil temp, etc. Right? So once you get to the desired setting, the engine is allowed to, or is ran so that it becomes stable. And then you take data, right? And it's typically X number of hundreds of cycles or 30 seconds of data that you average. But in doing so, you end up throwing away a lot of the dynamic features of the or dynamic behavior of the engine. And in the case of the dynamic DoE, the engine and all of the calibration variables is slewed simultaneously, and data is taken throughout this transient or dynamic process. So you end up getting a lot of data. But in order to enable this dynamic test, there's a few very important things that you need. You need first very fast communication access to the ECU. On the test facility side, a very highly transient low inertia dynamometer is required. You need sensors and measurement equipment that can react quickly. This includes things like emissions benches that are co-located close to the engine so that you can minimize the response time. So there's quite a bit of configuration that's required in order to be able to successfully carry out a dynamic DoE calibration in the test cell. Another question is, have you applied these techniques into electrified powertrain applications arena, such as battery or inverter modeling? So the answer to that is we are actually in the middle of doing that work right now, where we're setting up a plug-in hybrid powertrain in our test cell and calibrating it such that we're doing the entire system instead of just an engine-only operation. So as the industry moves from doing like a base calibration of an engine or a base calibration of a transmission in a test cell, and then moving into the vehicle, dynamic DoE lends itself to this process where we can do a lot of the calibration work in the test cell, saving the need to build new vehicles and that, and then it allows us to run the engine almost, or I guess run the powertrain almost like it was in the vehicle on the road. And we get very high quality data that is very indicative of how it would operate. And that, then the next step is beyond that is perhaps it's just you can forego the vehicle calibration altogether, or it's just a validation exercise in the vehicle. And that's the benefits of the dynamic DoE. And with the complexity of the system and hybrid systems, we're going through that exercise right now to see how we can adopt the process to a fully electrified powertrain system. So looks like that's the majority of the questions. If you have questions afterwards, or if I didn't get to one of your questions, please feel free to reach out to me directly. My email address is chi.la, so chi.la@iv-usa.com, and I look forward to discussing this topic further. Okay, thanks a lot, and everybody take care and stay safe.